Okay, everybody, what we're going to be doing in this video is we're going to be going through the June 2024 Regents exam. So if you go on NYS, actually I'll just put a link to it in the video description. But what you're going to do is you're going to go to the June 2024 Regent, click on examination, and we're going to go through each of the questions on here. I'm going to explain exactly how you can answer each one of these. Okay, well if you take a look at the first question, the first one asks you which quantity is a vector. And what you need to remember is that vector quantities are those that have a magnitude, in other words, a value, right? Magnitude is just like a fancy way of saying something has a value, and a direction, right? So vectors have direction. So if we look at our options here, we have electric field, electric potential difference, charge, and electrical power. Well, the only one here that's going to have a direction is going to be the field, because what you need to remember is that electric fields, we have positive and negative charges first of all, right? And electric fields show the direction that a positive charge would go or would move in the presence of those electric charges. So if I have a positive charge here, let's say it's a proton and a negative charge here, maybe an electron. If I put another positive charge right here, well, that positive will be repelled by the positive and pushed toward the negative. So electric fields always have a direction of going out from the positive and into the negative. You're going to have to keep that in mind, out from positive into negative for electric fields. And that's always going to be the case. The other one's electric potential difference. That's just voltage, right? You can't have 5 volts left or right. You just have 5 volts. Charge, you can't have 5 coulombs to the left. You just have 5 coulombs. Same thing with power. You can't have 20 watts to the right. You just have 20 watts. Okay, our next one says, what is the magnitude of the eastward component of the velocity of an airplane flying at 612 kilometers per hour in a direction of 40 degrees north of east? Well, first of all, let's say here's east, right? And then we're going to be going 40 degrees north of that. So maybe something like this. Well, I drew it not quite 40 degrees, but you get the idea, right? Like here's a 40-degree angle, and we're going at 612 kilometers east. And we want to know what did it say, eastward component is. So right here, you see how we're going in a diagonal? Every diagonal is made up of a little bit of a positive in a vertical direction and a little bit of a horizontal direction, right? You can't have a diagonal without it pointing a little bit to the right and a little bit up, or maybe down if it's pointing down, or left. You know what I mean, right? You can't have it without having a little bit of a horizontal and a vertical aspect to it. So what we want to know is, well, what is the horizontal aspect to this thing? And it doesn't have to just be for for velocity. We could have the same exact type of question for a force, for an acceleration, really for any vector. So when you look at the formula for finding components, we have ax equals a cosine theta, and ay equals a sine theta. And ax stands for the horizontal component of any vector. X is horizontal. Think like a graph, right? On a graph, you have the x and you have the y vertices, or axes. So you have x is the horizontal and y is the vertical. So in your formula, it's the same exact thing. X is the horizontal, and then a is going to stand for any vector. Anything that has a magnitude and a direction. So velocity, force, acceleration, displacement, all of those can have use in this formula. We want to find the horizontal component. So let's plug our numbers in. We want to find ax, the horizontal component. A, anytime you're using these formulas, A is the diagonal, right? The resultant, we call that. So in this case, that's my 612 kilometers per hour. So for that, I plug in my 612 kilometers per hour, and then sine of my angle, right? Sine of 40 degrees. Let's do the math. Let's see what we wind up getting. And when you're doing this, make sure you're in degrees mode, right? Because you have to do 40 degrees, not 40 radians. But if you do the math properly, you'll wind up getting 393 kilometers per hour, which you see at the top over here is option number 1, 393 kilometers per hour. Okay, we have a car initially traveling at 25 meters per second, and it's uniformly brought to rest as the brakes are applied over a distance of 40 meters. The magnitude of the average acceleration of the car while braking is blank. So every question you should always approach the same way, right? Write down what you know from the question, and then also write down what you don't know, and then find a formula that incorporates all of these guys. So it says it's initially traveling at 25 meters per second. So what I'm going to say is VI, my initial velocity, is 25 meters per second. It's uniformly brought to rest. At the end, right, we're brought to rest. So I know my final velocity at the very end is 0 meters per second. And that happens over a distance of 40 meters. So D, we're going to write as 40 meters. Then it says the magnitude of the average acceleration of the car while braking is blank. So they want me to find acceleration. Now, sometimes students get a little confused with that word average, right? If they ask you to find the average acceleration or the average force, I wouldn't stress that so much. The only time that really matters is when you're dealing with an average velocity, because that has a specific use, right? It has that formula where it has the little line over it for V, right? Average velocity. But for average acceleration, for average force, that's really just done to cover all bases, because if it wasn't a uniform acceleration, or if it wasn't a uniform force, which in this case it is a uniform acceleration, so they didn't really mention it, really what I'm getting at is don't worry about that word average. We're just finding the acceleration. So what we want to do now is find a formula that incorporates all of these. So here's your reference table, right? The 2006 edition, the reference table, the exact same one that you're going to be getting on the day of your Regent exam. And what you want to do is you want to go, if you're dealing with stuff about motion, everything regarding what we call mechanics, which is basically all about motion in the physical world, right, has to do on, has its place on the last page. So what we're going to do is we're going to find the formula then that incorporates all the variables that we have and also that one that we're looking for, right? So we're looking for acceleration. Let me just fix that, right? We want to find acceleration, and we have initial velocity, final velocity, distance, and acceleration. We're looking for acceleration. But what we can't do is we can't pick one that has time then, because we don't know what time is. So that's what I see a lot of students do a lot of times, right? They'll try to find acceleration, like for example using this formula. Acceleration is in there, so yeah, maybe you could solve for it. We have initial velocity, we have final velocity, but we don't have time. So that's going to put us in a tricky position if we try to use that, because if we don't know time and we don't know acceleration, then how are we going to solve for it? You could try, you're going to have two unknown variables though, and you're not going to be able to get anywhere. So you need to find a formula where the only thing that you don't know is that thing that you're looking for. Or excuse me, that the only thing you don't know is that one thing in the formula that's unknown. So in this case, we know final velocity, we know initial velocity, we know displacement or distance right here, d, and we want acceleration. So in this formula, we know everything except for that one thing we're looking for. We know everything except for our acceleration. So let's try that formula out. So again, what we're looking at is Vf squared equals Vi squared plus 2AD. We'll plug in all of our values. Vf is 0, so that becomes 0 meters per second, and we square that, equals Vi, which is 25. So we plug in again 25 for Vi, squared because it's Vi squared, plus 2 times A. I don't know what A is, right? So I can't plug a number in, so I leave it as A, times D. D is 40. So we plug that in for that. Now we just have to simplify, right? 0 squared is 0. 25 squared, is that 625? Let me check. Yeah, that's 625. 2 times A times 40. Well, that's just going to give us 80 times A, right? Because 2 times 40 is 80 times A. We just have the A still there. We want to get A alone now. So we're going to move our 625. Right now it's involved in addition. It's 625 plus 80A. We can't just add 625 and 80, right? Because they're not like terms. This has a factor of A attached to it. So we need to move this 625 away, and it's involved in addition. So we'll do the inverse operation and subtract it away on both sides. We get then negative 625 is equal to 80 times A. And again, you do the inverse operation. Now we want to get A alone. 80 times A, divide away the 80, right? Division is the opposite of multiplication, so you divide that thing away. 625 divided by 80. Let's see what that is. That's going to give you 7.8 meters per second squared. Meters per second squared, because that's what we measure our acceleration in. And there you go. So our next one, a brick starts from rest and falls freely from the top of a building to the ground. As the brick falls, its acceleration blank. Well, this one, if you remember what we talked about with gravity, this one should make sense. Gravity, remember, is a constant value of 9.81 meters per second squared, right? That's probably the number that you have drilled in your head from this class that you'll never forget. right, gravity accelerates every object toward the ground at a rate of 9.81 meters per second squared. And what that means is that every second that passes, a falling object gets faster by 9.81 meters per second every second. So it's meters per second per second. That's why it's meters per second squared. And that's what our acceleration is. Now that's a constant value for every object on Earth. Doesn't matter about the mass, doesn't matter about the size, doesn't matter about the density, doesn't matter about anything, right? Assuming that we're in a vacuum, right? Assuming we have no air resistance or anything like that. So as the brick is falling, its acceleration remains constant at 9.81 meters per second squared. And we're going to be getting faster, right? We know that as objects fall, they get faster and faster and faster and faster. So our acceleration is constant, and our speed increases, which would lead us to option 3 there. Constant acceleration, but an increasing speed. Here's another one that, if you remember what we talked about with inertia, shouldn't be too bad, right? This one I definitely want you to remember, because if you see a question like this, you're going to get it for free. As long as you remember this one thing. Replace the word inertia with the word mass. They're essentially, for our purposes, going to be the same thing. They aren't the same thing. There's slight differences between them. But for our purposes, every time you see the word inertia, just replace it with mass. So if this question is asking you which one has the greatest inertia, reword that to which object has the greatest mass. Well, obviously the 2,000 kilogram truck is going to have the greatest mass. The speed has nothing to do with your inertia. Only the mass. So option 4 here. Next one, an unbalanced force is always necessary to keep a body at rest, keep a body moving with a constant velocity, change the speed of a body, or change the position of a body. So when we're talking about an unbalanced force, right, you could have forces acting on stuff, but they don't necessarily have to be balanced. For example, let's say there's a box right here, and here's someone pushing it. And that person is pushing this box maybe with, 20 newtons of force. That would be an unbalanced force. Right? There's nothing balancing it out. There's nothing canceling it out, in other words. But let's say you're coming along here and you don't like me moving the box. So you come along and you push it the other way with exactly 20 newtons. Now these two forces are balanced. And what we call that is a state of equilibrium. Keep that word in mind, right? Equilibrium. It means all of the forces acting on the object are balanced out, and therefore they're going to have no acceleration. Where do we get that principle? Well, it comes from Newton's second law. Newton's second law tells you that the net force, in other words, the total force, the sum of all the forces acting on an object, is equal to the mass times the acceleration. In a state of equilibrium, if these forces cancel out, which they are in this equilibrium example, that means your net force, the total force, is 0, which means your mass times your acceleration. Well, the only way you're going to get 0 force is if your acceleration is also 0. So equilibrium, what you have to remember is that the sum of forces is 0. In other words, the net force is 0. And that means that you have 0 acceleration. So 0 newtons for the net force. And then acceleration is also equal to 0 meters per second squared. But that's not the case in this question, right? This question, they're telling us that we have an unbalanced force. So that's the example, again, where I'm just coming along and I'm pushing that really heavy box with, let's just put another number on. Let's say 50 newtons of force. I'm pushing that box with 50 newtons. Well, that's an unbalanced force, so we're not in a state of equilibrium, meaning our acceleration is not 0. We have a non-zero acceleration. Again, if we bring it back to Newton's second law, F net equals m times a, well, here my net force is 50. The box has to have a mass. Let's just say that the box is 10 kilograms. I don't know. So we have a 10 kilogram mass. Well, the only way that I'm going to get a net force, as per the math of this formula, is if my acceleration is not 0, right? I have to have a 5 meter per second acceleration for this particular example that I just came up with. What I'm getting at here, though, is that if you have an unbalanced force, that has to result in an acceleration as per this formula. You can't have a non-zero value for this and a 0 value for this. So you have to have an acceleration whenever there's an unbalanced force, meaning that there has to be a change in the speed of the object. Acceleration is the change in velocity or the change in speed over time. So that means option 3 is going to be the one that's correct here. A change in the speed of the body. Space probes launched from Earth send information back to the Earth from space in the form of mechanical waves, sound waves, longitudinal waves, or electromagnetic waves. Well, for this one, if we're sending information in the form of waves through space, remember space is a vacuum, meaning we don't have a medium. A medium is something that wave moves through. But if we're in space, there is no medium, and the only type of wave that can move without a medium would be an electromagnetic wave, right? Like light, for example. Light doesn't need a medium. Light from the sun comes over to Earth, and it moves through space without anything, without it having to move through anything. So electromagnetic, remember, is the only one that moves without a medium. So here, it's 4, electromagnetic. A ball is thrown from level ground at an angle of 55 degrees above the horizontal and lands at level ground. Neglecting friction, if the ball is thrown again at the same angle but with a larger initial speed, the ball will travel blank. Higher with the same distance horizontally, to the same maximum height and a farther distance horizontally, both farther and higher horizontally, or to the same height and the same distance. Well, this one we could prove with the math, right? We could prove with our formulas AX equals A cosine theta and AY equals A sine theta, right? Because if we have a larger value for A, a larger initial velocity, we're going to get a larger horizontal component, which makes us go farther horizontally. And we're also going to get a larger vertical component for our velocity, which makes us go higher vertically. Well, you don't even really need to think about it in terms of the math. Just think about it logically. If you throw something harder and faster, it's going to go farther, right? If you throw something harder upward, it's going to go higher up. If you throw something harder vertically and horizontally, it's going to go farther horizontally. If you throw something harder and you're throwing it diagonally, it's just going to go farther in both directions. So both higher and farther horizontally. A photon collides with an electron as represented in the diagram below. After the collision, the electron recoils and the photon is scattered in another direction with a longer wavelength than the incident photon. The increase in photon wavelength results because during the collision, the photon blank. Well, let's look at our options first, actually. It says it loses energy to the electron, it gains momentum from the electron, it loses some speed, or it generates a magnetic field. Let's think about what we mean in terms of wavelength and photons here, right? We have the formula, E photon. The energy of a photon is equal to Planck's constant times the frequency, which is also equal to Planck's constant times the speed of light over the wavelength. Well, we just said that we increased our wavelength, right? Larger wavelength. So this gets bigger. Well, if we increase the wavelength, well, then we're dividing then by a bigger number. If we're dividing by a bigger number when we do the math, we're going to wind up getting a smaller value for our energy of the photon. So the only way this makes sense is if you get a larger wavelength, you get a smaller energy. So that means that we had to have lost energy in some way. So option 1, you lose energy to the electron. Okay, here's one you're definitely going to have to remember, right? What is the weight of a 60 kilogram student on the surface of the Earth? There's not a formula directly telling you what this is, but I'll show you on the reference table where you can find this information. So looking back over here on our reference table, it tells you right here that Fg is the weight or the force of gravity. Those are the same thing, right? All weight is the force of gravity acting on an object. So if we want to solve for Fg, well, formula with Fg is this one right here, but never use that one to find your weight, right? This is not the weight formula. This is the formula you want to use if you want to find how much two objects are pulling on each other, right? Maybe like Mars and Earth. Right? How much force of gravity there is between two masses. But if you want to just find the force of gravity acting on a single mass, you're looking at this formula right here. Fg divided by m equals g. Or the way I like to write it, Fg equals m times g. Right? It's a little bit easier to remember, I think. Fg, the force of gravity, or in other words, your weight. Remember, this is your weight, is equal to mass times the acceleration due to gravity. You have to remember g is the value of 9.81 meters per second squared as long as you're on Earth, right? Maybe they'll give you a question where they say, find the mass and the weight of this thing on Mars. If they do that, they're going to have to tell you what the value of g is on Mars. But it's assumed that you know that the value of acceleration is 9.81 meters per second squared. If for some reason you forget that, right, all of your constant values are always given to you on the front page of the reference table. So if you did forget that G is 9.81, it's given to you right there as well. So if we look over here again at our formula and our question, we have a 60 kilogram mass. So mass we're going to plug in as 60 kilograms times 9.81. You do the math for that, you're going to get 589 newtons, which is option number 4. Keep that in mind, how to solve for your weight. Don't forget that. Mass times 9.81, kilograms times 9.81 gives you your weight, or at least on Earth. Here we have a 120 Newton box pulled by a 48 Newton force across a horizontal surface at a constant velocity. The coefficient of kinetic friction between the box and the horizontal surface is blank. Well, the coefficient of friction is that funny looking symbol mu. Coefficient of friction here is what they're telling me to find. So I want to find what the value of mu is. What I know is that this box is 120 newtons. Remember we were just saying your weight can be measured in newtons, or it should be measured in newtons. So what they're saying in this question is that the weight, the force of gravity, is 120 newtons on that box. And we're pulling it with a force of 48 newtons. So here I am, maybe it's attached like a rope, and I'm pulling it this way with 48 newtons of force. What I do know is that we're going at a constant velocity, meaning we have no acceleration, meaning that there has to be equilibrium. Remember we were talking earlier about what equilibrium means, right? Over here, equilibrium means that your acceleration is 0, no change in velocity, which means your net force has to be 0, meaning your forces have to cancel out. So right here, I'm pulling with 48 newtons. In order for me to be at constant velocity, I need to be in equilibrium, and there needs to be 48 newtons going against me. That 48 newtons is going to be coming from the friction between the object and the ground below it. So what we could say is that my friction is 48 newtons. And then I want to find mu. So again, we'll look at our formulas. Remember, if this is dealing with motion, look at all the formulas regarding motion. So we'll jump back over to our reference table and we'll look at all those formulas that involve stuff about motion and forces. So right here, this is the only place where you're going to see the coefficient of friction appear. FF equals mu, coefficient of friction, times Fn, the normal force. So then what's the normal force? Well, the normal force is what keeps you from falling through your chair, right? If you're sitting in your chair, let's say here you are, and maybe, I don't know, let's just say you're 600 newtons. You're applying a downward force of 600 newtons onto that chair. The reason you're not falling through is because the force is applied back at you as per Newton's third law, right? Every action has an equal and opposite reaction, pushing back up against gravity. And that's what we call the normal force. The force that goes against, equal, and opposite to the force of gravity. So it's the same exact thing as your weight. All you have to remember then is that whatever your force of gravity is, whatever your weight is the same thing as your normal force. Assuming you're on a flat surface, which for our purposes, you're always going to be on a flat surface in these questions. So then we could use our formula, FF equals mu times Fn. I kind of wrote out of order. It's okay. Right? Fn times mu, or mu times Fn. We'll plug in our numbers, and we have 48 newtons for the force of friction, 120 newtons for the normal force, and then your mu is what you're going to solve for. You want to get mu, so you divide by 120 on both sides to get it alone. 48 divided by 120, I'm assuming that's going to be 3, but let me double check. See that? That's why you always double check. If you do 48 divided by 120, you wind up getting 0.4. So it's option number 2. And the coefficient of friction is unitless, right? This doesn't have a unit to it. It's not 0.4 meters per second. It's just 0.4. So the coefficient of friction in this case, option 2, 0.4. Box A has a mass of 10 kilograms and is at rest on a shelf that is 1.5 meters above the floor. Box B has a mass of 20 kilograms and is at rest on a shelf 3 meters above the floor. Compared to Box A, Box B has a gravitational potential energy relative to the floor that is blank. Well, we could solve for that, right? If we know our formula for gravitational potential energy, which is PE equals mgh, we could solve that for both A and B, right? Box A says that we have a mass of 10 kilograms. So we have potential energy is equal to 10 kilograms times g, right, 9.81, times the height, 1.5. Do the same thing for B. We'll compare our two numbers. Right? B, it says that we have a mass of, what does it say, 20 kilograms. G just stays as G, right? It's still 9.81 meters per second squared. I forgot to put my units here, right? Don't make the same mistake I just did. Put your units, meters per second squared. And times 3 meters. Okay. Now you don't have to go through doing all this math, right? You could do it in your head if you know how to do that quickly. But if you're not sure, you could always just do the math and figure out what the number is going to be that way. Well, let's figure out what that is. So for object A, you get 147.15 joules, and for object B, you get 588.6 joules, which this is 4 times greater than this is. So compared to box A, box B has a gravitational potential energy 4 times as great. So option 4. A 0.1 kilogram yo-yo is whirled at the end of a length of a string in a horizontal circular path of a radius 0.8 meter at a speed of 6 meters per second. The magnitude of this centripetal acceleration of the yo-yo is blank. Again, let's just start every question the same way. Let's write down what we know. We know that our mass is 0.10 kilograms. We know that the radius of it is 0.8 meters. And we also know that the speed of it is 6 meters per second. And then they tell me to find the centripetal acceleration. Centripetal acceleration is AC. So we're trying to find AC here. Let's look at our formulas and see where centripetal acceleration appears on that formula sheet. Again, we're dealing with motion. So think about those ones at the end of the reference table, right? All of these guys right here. AC, we'll find on here, is equal to, where is it? Right here. AC is equal to V squared over R. So all you have to do then is just V squared, speed squared, divided by R, the radius. So let's go ahead and try that out. We have AC equals V squared divided by R. Therefore, that's going to become 6 meters per second. Square that. Divided by 0.8 meters. 6 squares 36. 36 divided by 0.8. Let's see what that is. And when you do that, you wind up getting 45 meters per second squared. So option 4. Okay, we have a 4 kilogram mass initially at rest on a horizontal frictionless surface. A constant 2 Newton force to the east is applied to the mass for a 5-second interval. As a result of this action, the mass acquires a blank. So what you need to remember here is that if you see a force, specifically like the only force, a net force, or in other words, only one force mentioned, and you also are given a time, think about impulse. Impulse is one that's kind of forgettable, but all impulse really means is the change in momentum of an object. Right? We also know that we have a mass of 4 kilograms in this case. But impulse is defined as the change in momentum, and impulse is represented by J. And on your reference table, we're given F net times time is equal to impulse. It's also equal to delta P. And I always tell you to tack this on at the end. It's not going to be important for this question, but maybe in the future, right? It will come up in this test. We'll see. Mass times the change in velocity is another part that isn't given on the reference table, but you should remember you can add on to this right here. So what we have here is that impulse is equal to your force times your time. And that impulse is the change in momentum. So if we have an impulse of 2 newtons times 5 seconds, in other words, 10 newton seconds, that means we have a change in momentum of 10 kilograms meters per second. So our answer is going to be, oh, actually we have 2 of them, right? We have momentum of 10 kilogram meters per second east and west. Well, in this question, we were pushing the box to the east, I believe it was. Let me double check. Yes, a constant 2 Newton force is applied east. So if I'm pushing the object east, then I'm going to gain my momentum in the eastern direction. So it's going to be 3, a momentum of 10 kilograms meters per second east. Okay, here's one that's going to be straight use of one of our formulas. It says a motor lifts a 1.2 times 10 to the 4 Newton elevator. So let's write down our value. We know our force is 1.2 times 10 to the 4th newtons. And we lift it 9 meters, so our distance is 9 meters, in 15 seconds. So your time is 15 seconds. And they want you to find the minimum power output. So they want you to find P, capital P, power. Lowercase p is momentum, capital P is power. So let's look at our formulas for power, right? Because we only have one section about power on here, right at the bottom. Actually, that's not true because we do have electrical power as well. But if we're dealing with just like the physical, mechanical idea of power, we're looking at these down here at the bottom. P is equal to work over time, or P is equal to force times displacement over time, or P is equal to force times the average velocity. Think about what you have here. You have force, you have distance, you have time. So if we do power is equal to force times distance over time, we can get our power value. So let's go ahead and try that. We'll write down our formula, right? P is equal to FD over T. So we have 1.2 times 10 to the power of 4 newtons times 9 meters divided by 15 seconds. Plug that into your calculator and we'll see what we wind up getting. So I got 72,000 here, which if you look at your options, that would be 7.2 times 10 to the 3rd power, right? 7.2 times 10 to the 3rd power. Actually, now I'm looking at it. Is that right? No, it looks like I made a mistake somewhere in there. Must have put the wrong power of 10. I'll double check my work, but 7.2 times 10 to the 3rd means you move that 1, 2, 3. So I should have gotten 7,200. Let me double check what I did wrong for this one. Okay, I figured it out. When I did 1.2 times 10 to the power of 4 in my calculator, I accidentally did 12 times 10 to the power of 4, so I got an extra 0. So 7,200, or in other words, 7.2 times 10 to the 3rd power. A train blows its horn, which emits a uniform sound as the train approaches a stationary observer. The observer hears a sound that is, so we either have lower frequency or higher frequency. So let's start with that. If the train is approaching you, well, the Doppler effect comes into play. Doppler effect says that as a sound source moves toward you, all those waves, those sound waves that it's emitting, kind of get squished up, as you can see in this little picture right here. Right? Those sound waves are getting squished up as it comes toward you, which is going to result in a higher frequency. If it's moving away from you, if you're on the back end of it, right on the back side where it's moving away from you, then all those waves are getting spaced out and you'll get a lower frequency. So since the train in this example is moving toward us, like how we have this person over here on the left standing as a stationary observer, that frequency is greater. We have an increased frequency. Then we have to figure out the amplitude, because you see 3 and 4 both talk about higher frequencies. So if the train is coming toward you, amplitude relates to the volume. If the train's coming toward you, you know the volume is going to be getting greater. So we have option 4, a higher frequency and an increasing volume, or in other words, an increasing amplitude. A wood block is pulled at a constant velocity across a horizontal wood floor. Which type of energy increases as the block floor system moves? So gravitational potential energy wouldn't increase because it specifically says that we're on a horizontal floor. The only way your gravitational potential energy increases, as per your formula, is if your height is changing. But I'm not changing my height, right? I'm on a horizontal floor. Next one says kinetic, right? Option 2 says kinetic. Well, kind of the same idea right there, right? As per your formula, Ke equals 1/2 mv squared. The only way your kinetic energy is changing is if your velocity or your speed is changing. It says right in the question that we're going at a constant speed, constant velocity, so we're not changing my kinetic either. Mechanical energy, mechanical is the sum of these guys, as well as Q, internal energy. But that's not really going to be a factor here, right? Mechanical, actually no, excuse me, Q is not considered one of those forms of mechanical energy. Just potential and kinetic energy. Forget what I just said. Potential and kinetic energy, as the sum of those, is your mechanical energy. So if neither one of them changes, the sum of them together doesn't change. Last one, thermal energy, right? As I'm dragging that box on the floor, I'm generating friction, which is going to generate some heat, which means that my thermal energy is increasing. So option 4. Okay, a total energy of 5 joules, so we know that the energy is 5 joules, is used to move an electron from position A to position B in an electric field. Okay, so we're dealing with electricity here. Well, electricity, if we're dealing with energy and electricity comes up, I'm going to show you something on your reference table. Because on your reference table, they have a whole specific section all about electricity. Let's see. Right, electricity has its own page right over here. Oh, let me move this question. There you go. Right, so electricity has its own page right here. And what you see is that the only form of energy right here is W, electrical energy. So we know that they're giving us W then. And then they're telling me to find potential difference. Right, potential difference you see right here is V, the voltage. So that's what I'm trying to find. So if I have W and I want to find V, V and W come together in this formula right here, right? V is equal to W over Q. Well then, I need to know Q. Q, you see, is charge. Well, I'm going to tell you, you know the charge here. If you look at the question again, the question specifically says that we're dealing with an electron. Well then, what's the charge of an electron? When in doubt, check your reference table. Right front page, they'll tell you what the charge of an electron is. Somewhere over here. Elementary charge, here you go. Right, the elementary charge, the charge of either an electron or a proton, right? A proton and electron have the same charge. One's positive, proton, one's negative, electron. So Q, in other words, our charge in this question is going to be 1.6 times 10 to the negative 11. So let's write that down. Technically, it's going to be negative 1.6 times 10 to the... Oh, did I say negative 11? I meant negative 19. Negative 19 coulombs, as per the front page of your reference table. And remember, we said our formula is V is equal to W over Q. You plug in your numbers. You have 5 joules, and you have 1.6 times 10 to the power of negative 19 coulombs for your charge. Let's do the math and find out what that value for V is going to be. And if you do your math, what you'll wind up getting is that V is equal to 3.1 times 10 to the power of 19, and that would be in volts because it's a voltage, a potential difference. So option 1. Okay, a 0.14 kilogram lacrosse ball traveling west at 17 meters per second is brought to rest with a 0.21 kilogram lacrosse stick. If the force applied by the lacrosse stick on the ball is 220 newtons east, the force applied by the ball on the stick is blank. So we have, I don't even know what a lacrosse stick looks like, so let me look that up real quick. Okay, so it's kind of like a net. I don't know, I never played lacrosse. So we have a lacrosse stick applying a force onto this ball. And it applies a force onto it, it says, of 220 newtons. Well, when it hits that ball is going to apply that same force right back at it. 220 newtons right back at the stick. Why is that? Well, again, Newton's third law. If you apply a force onto something, right? So if I hit the table's hitting me back. If the stick hits the ball hits the stick back. And Newton's third law tells you that that force, that reactive force, is equal in magnitude. So if I hit the wall with 20 newtons, the wall hits me back with 20 newtons. If the cross stick hits the ball with 220 newtons, then the ball hits the stick with 220 newtons. So it's just Newton's third law. You don't actually have to do any math here. But you do have to get east and west right here. So you hit the ball with 220 newtons east with the stick. Actually, I drew this backwards then, right? Because, well, let's say this is the... Yeah, I did draw it backwards. But the stick applies the force east. The ball then has to apply it back at it west, right? Same thing right here. If I push on the wall to the right with F1, the wall pushes backwards with F2 in the opposite direction. So equal and opposite forces. Okay, 4 wires are tested for electrical conductivity. All the wires have the same length and the same cross-sectional area, but are made of different metals. Which wire has the highest conductivity at 20 degrees Celsius? Okay, if we're dealing with the resistance, the conductivity of different metals, and we're talking about the cross-sectional area, what we're looking at is this resistance formula. The resistance of a wire is equal to the resistivity, little p, called rho in Greek, times length over the area. They all have the same area. They all have the same length. So those don't really matter. So what we want to look at is the resistivity, which let's take a look at our reference table, right? Again, on your reference table, we have a little information about everything. So on your front page, no, not the front page, excuse me, on the page about electricity, we have this table right here that talks about the resistivities. So if we want the highest conductivity, what we want is the lowest resistance. In other words, we would want the lowest resistivity here. So look at your 4 options and then figure out which one is going to have the lowest resistivity and therefore the lowest resistance, the highest conductivity. Aluminum is excuse me, 2.82 times 10 to the negative 8. Copper, 1.72. Gold, 2.44. And silver, 1.59. So you see 1.59 is the smallest of those. So silver is going to be the lowest resistance and therefore the best at conducting electricity. Conducting meaning it allows that electricity to flow through it. So your option here is 4. Okay, the angle of incidence for a ray of light striking a plane mirror is 20 degrees. So here's your mirror. Light's coming in, makes an angle of 20 degrees. Now where are we measuring that 20 degrees to? We always measure our angles to the normal. This is not 20 degrees. I drew it inaccurately, but that's fine, right? Let's just say it is 20 degrees. If I made it 20 degrees, it'd be too small to really write in the 20. So maybe it worked out for the best. What we want to know is then what is the angle between the incident ray? Incident means the light that's coming in. Incident, right? To be incident on something means to strike something. So it's the incident one, the one that's striking the mirror. And then the reflected ray. So we know that it reflects off of the mirror. Well, the angle of reflection is always the same as the angle of incidence. So whatever you're coming in with is the same as what you're leaving with. Right here, we want to know the angle between the incident and the reflected ray. So don't write 20 as your answer just because the reflected ray is going at a 20 degree angle. We want the angle between these two, which 20 and 20 would give you 40. So option 2.